Hey everybody, welcome back for another chemistry lesson. Today we're going to talk about specific heat capacity and calorimetry. So when we use the term heat in chemistry, we are talking about an exchange of thermal energy between a system and its surroundings. And heat exchange happens when there is a difference in temperature between those two things. Reminder, temperature is the measure of thermal energy in a sample of matter. And so heat is going to flow from the matter that has the higher temperature to the matter that has the lower temperature until both objects reach the same temperature, which is what we call thermal equilibrium. So when a system is absorbing heat, its temperature increases. That's why the temperature of water in a pot on a stove increases, right? Because we are putting energy into that system. The increase in temperature is directly proportional to the amount of energy or the amount of heat that is absorbed. So we have a proportionality constant, which we call the heat capacity, and we use the letter C, it's a capital C, to represent heat capacity. The units of C are usually joules per degree Celsius or joules per Kelvin. It doesn't actually matter because a degree Celsius is the same size as a Kelvin. So a change of 1 Kelvin is a change of 1 degree Celsius. So it only matters because you need to be aware of it so that your units cancel out. That's it. And reminder, Q is our heat. All right. The larger the heat capacity of the object that is being studied, the smaller the temperature rise will be for a given amount of heat. Right, so the heat capacity of an object totally depends on the amount of matter in that object, and we usually measure this as mass. So 200 grams of water is going to take twice as much heat to raise its temperature by 1 degree Celsius as 100 grams of water. Hopefully that's pretty commonsensical. And the heat capacity of an object also depends on the type of material. So 1,000 joules of heat energy is going to raise the temperature of 100 grams of sand by 12 degrees Celsius, for example, but it's only going to raise the temperature of 100 grams of water by 2.4 degrees Celsius because it takes more energy to raise the temperature of water. So it is mass dependent and, well, matter dependent, but we measure it as mass, and substance dependent. All right, so we also use the term specific heat capacity, which is the measure of a substance's intrinsic ability to absorb heat. All right, the specific heat capacity is the amount of energy required to raise the temperature of that substance, 1 gram of it, by 1 degree Celsius. So we use the heat capacity, C, with a subscript of S for specific heat capacity. And so because we're using it for a specific mass, the units for this are joules per gram times degrees Celsius. So this, previously the heat capacity only talked about the amount of energy and the change in temperature. Here we're talking about for a specific amount of mass. All right, and then the molar heat capacity is the same idea, but for 1 mole. The specific heat capacity is what you're most likely to see. And here are some reference numbers for you, right? So the bigger the number here, the more energy it takes to change the temperature of that substance, right? So lead, all of our metals down here have pretty low specific heat capacities. Water is really, really high compared to these. So that means that lead, I can heat it up really quickly with a smaller amount of heat because it's very easy to change the temperature, whereas it's very hard to change the temperature of water. This is why sweat works. All right, so when we are quantifying heat energy, the heat capacity of an object is proportional to, again, the mass of the object and then the specific heat of the material that we're dealing with. So we can calculate the amount of heat absorbed by an object if we know its mass, its specific heat, and how much the temperature changed, because there's a formula for that. So heat is equal to mass times the specific heat capacity times the change in temperature. It does not matter where we start or where we end. We're looking at how much does the temperature change. All right, so this is actually really important climatically speaking. Water can absorb a tremendous amount of energy without a big increase in temperature because it has such a high specific heat capacity. So what that does is it keeps the air cooler by large bodies of water, so like at the beaches. So for example, the temperature difference in the summer in Sacramento, which is in inland California, versus San Francisco, which is right here on the water, can be as much as 30 degrees Fahrenheit. I'm sorry, we're American. That's how our Weather Channel does it. Or 18 degrees Celsius. That is a huge difference. It is the difference between sweating to death, that would be me at 100 degrees, versus being very comfortable even in jeans in the sun at 70 degrees. Again, sorry, I know that's not very sciencey when I'm talking about temperature in Fahrenheit, but the Weather Channel does it. So because of this huge heat capacity of water, it's commonly used as a coolant and can absorb a ton of heat and remove it from whatever important mechanical parts to keep them from overheating. It can even prevent melting of things, and it can be used to transfer heat to something else because it's a fluid. So let's talk about this in a chemistry lab. So when two objects at different temperatures are placed in contact, heat flows from higher temperature to lower temperature. That is a law of nature. It always works that way, right? So because we know about the law of conservation of energy, we know that the amount of heat or thermal energy that is lost by the hot thing is equal to the amount of heat that is gained by the cold thing. Because we're talking about, again, thermal energy, law of conservation of energy. So let's think about this specifically. All right, we've got a block of material, a metal, at 55 degrees that gets put into water that's about room temperature, initially 25 degrees. This thermal energy is going to transfer from the hot thing, the metal, to the cold thing, the water, until we get to thermal equilibrium. And exactly how much that temperature changes depends on how much metal there was, the mass, how much water there was, the mass of that, the specific heat capacities of both of those things. You probably don't remember, but in the previous slide where I had the specific heat capacity reference numbers, lead was like 0.1 something, aluminum was 0.9 something. Well, that's going to be a really big difference in how much the temperature changes. So it all depends on that. And so what we can do is, because we know that heat lost by metal and heat gained by water have to be equal and opposite of each other, we can set them equal and opposite of each other in our equation, the Q equals mc delta T equation, and we can just have that on both sides of our equal sign. Important piece of information. We can also do work through volume change against an external pressure. This is like a piston, so this is how that works, right? So just keep in mind that work is equal to external pressure times the change in volume. Now, we know that an exchange of heat energy, which is Q, and an exchange of work, which is W, is all happening in between the system and the surroundings, and this is where our energy change happens. So remember, change in volume. We can determine our delta E by measuring Q and W. In a chemistry lab, it is easiest to do this so that we don't have a change in volume. If we don't have a change in volume, that eliminates the work portion, and we can say that the change in energy of the system is equal to the heat that we calculated. All right, so in practice, I can't observe temperature changes of individual chemicals that are involved in a reaction. So instead, we measure the temperature change in the surroundings, right? I don't have a thermometer that's like injected into a piece of metal that can measure the temperature of that metal. So what I do is I can control the surroundings and insulate it. All right, so in the high-tech world, we use what is called a bomb calorimeter. It's usually made of a sealed, insulated container. You fill it with an exactly known amount of water, and then we can safely say that Q of our surroundings is equal to the Q of the calorimeter, which is negative Q of the system. So let me show you what that looks like. So this is a bomb calorimeter, right? We fill this thing with oxygen, fill this up with a known amount of water, and then it's sealed. And then what we do is we ignite this so that combustion takes place. Because I know this is insulated, and because I know exactly how much water I have, then I can say if the water changed by this amount of temperature, then I know exactly how much heat that is. And because it's insulated, the only option is it came from here. So the amount of heat lost by this is the exact amount of heat gained by this. That's a bomb calorimeter. Okay, so we call this process calorimetry, and we measure that heat exchange. The bomb calorimeter has a constant volume, which is this, and is used to measure combustion reactions. And then we can look at the heat capacity of the calorimeter and create a calorimeter constant for, let's say, 2 liters of water exactly, or whatever. In a general chemistry lab, in particular my general chemistry lab, we do coffee cup calorimetry. It's not as precise, but it does the same idea. We have coffee cups, we have a known mass of water in the coffee cup, we have a lid that insulates, and what we'll do is we'll put something into that, immediately put the lid on, and observe the change in temperature of the water. That's what most chemistry students get to experience. If you are doing some sort of analytical chemistry or a special project, you may get to use a bomb calorimeter, but essentially we can measure the temperature of the water very easily, just stick a thermometer into it. So by knowing that, we can figure out the other piece.